This is a video on section 6.4, a typical problem when it comes to working with integral defined functions. Okay, and to the left of your screen you are seeing a function f of t that has been given. Okay, and it's a graph of just something that kind of goes up and comes down, and it's sort of some sort of trigonometric function. Okay, but you don't know what the formula of this function is. Okay, and that's the point of this problem. But I'm going to take this given function and I'm going to make a new function. Okay. And the book typically calls this capital F of x, and we'll call this the integral from 0 to x of this f of t dt. Okay? So there is the plot that is shown, okay, and the new function that we have. Okay? And I want you to answer the following question. Okay? Can you find f of, say, 1.5 of this function, okay, f of 1.5, and can you give me, answer the question, is the answer going to be a positive or a negative number? Okay, so you've been given a function f of x, where you've been given f of t, and I just want you to answer the question, is the function of capital F evaluated at 1.5 a positive or a negative number? Okay. So take a second to pause this video and think about that question. Okay, if you've had a moment to think about this, the answer to this question is going to be because capital F of x is an area function, capital F of 1.5 means to compute the signed area under f of t from x is equal to, t is equal to 0 to t is equal to 1.5. So in this picture we can see that 1.5 is about here, and this function capital F of x means to find the signed area from 0 to 1.5. Okay? And all you have to determine is that number positive or negative? Is the area a positive signed area or a negative signed area? Okay? And the answer is that the answer is going to be some positive number. Okay? And there we go. That is the first question. The second question I would like to ask is, can you find f of 1.5 approximately? Can you give me a very rough estimate for what the positive number is going to be? Okay? A very rough estimate. Okay? If you could pause this video and try to formulate your answer to that. And I'll give you a hint that maybe a Riemann sum would be a good idea. Okay? Alright, so if you've had a moment to come back from this problem after thinking about it, I'm hoping that what you tried there was to do a Riemann sum, okay, and was to find the area of this box. Okay? We can see from the graph over here on the left that this function, okay, has a height of 1 and a width of 1.5. So the approximate answer for this, the function evaluated at 1.5, is approximately 1 times 1.5, which is equal to 1.5. Okay? And that's a positive number. Okay? So the next question. So we're just trying to get a sense of what this function capital F of x is. It's an area function. If you pick a number You can try to answer questions about whether or not that number is a positive or a negative, and you can get a sense of an estimate of that number. Okay? Answer the following question now. Okay? Because this function, capital F of x, because it's an area function, f of t dt, because it's a function, and we know, for example, that it's a function because when you put in 1.5 into this function, you get approximately 1.5. If you put a number in, you get some sort of number out. That's what a function is. Because it's a function, can you tell me what the derivative of this function is? It's a function, so we should be able to take its derivative. Okay? And the answer there is little f of x by the second fundamental theorem of calculus, part 2. Okay? So you should be able to answer the question now, what is f prime evaluated at 1 point, let's say f prime evaluated at 1. Okay? Can you find f prime evaluated at 1? Okay. I'll give you a hint that it is some number. That's what I'm looking for, a number. So take a moment to look at the graph on your screen here and see what its relationship is to finding f prime, capital F prime evaluated at 1. Alright, so if you've had a moment to think about that, after you've paused the video and had a moment to think, we'll go ahead and fill in the number. Okay, well, since f prime evaluated at 1 means the derivative of x with respect to x of f of x, and then evaluated at 1. That's the meaning. But we decided that the derivative of capital F is little f, and we're supposed to evaluate that at x is equal to 1, which means that capital F prime of 1 is the same thing as little f evaluated at 1. And according to this graph, little f evaluated at 1 is somewhere around, a little less than 1, so we'll call that around 0.8. So f of 1 is approximately 0.8. Okay? And we're doing all this estimating because we don't know exactly what this function f of t is. Okay? So what I want to do in the next part of the video, okay, is to kind of supply a specific formula for little f of t, and then we will put specific numbers to this problem and see how our estimates matched up. Okay, so let's do that now. Okay. So what if I were to tell you that that function f of t, okay, is the graph of sine of 2t? And therefore, the capital F of x function that we're looking at is the integral from 0 to x of sine of 2t dt. Okay? And now we have the opportunity to bring in, okay, a better graph of what's going on, something with specific numbers. Okay? And here what we are seeing is the graph, big F of x is an area function. So what we're seeing on the screen here to your left is that sine of 2t is the dotted line, and capital F of x is the solid line that you're seeing on the graph. Okay? And let's see if that makes sense. Okay? We've got two graphs, a dotted line, which is the graph of sine of 2t, and then as you change the upper limit, right? Okay. Now what we're seeing on the screen is what is capital F of 1. Can we see that? Capital F of 1 is the red shaded region, right? Or it's the red shaded region under the dotted line graph, or it's the red dot on the solid line graph. Okay? You see that? So f of 1 is the area function. It's the area under the dotted line function from 0 to 1. Okay? And according to this picture, we're seeing that it's around f of 1. You know, we said it was about 0.8, but we're seeing here that it seems to be somewhere around 0.73, maybe closer to that. So it's a more refined estimate. Let's figure out what f of 1 is exactly. Okay. It would be the integral from 0 to 1 of sine of 2t dt. Okay. Find the antiderivative of sine of 2t, which would be the derivative of cosine is negative sine, so negative cosine of 2t divided by 2 is the antiderivative, and then evaluate from 0 to 1. So you'll get negative 1/2 cosine of 2 minus negative 1/2 cosine of 0. And therefore you get 1/2, negative 1/2 makes a positive 1, 1/2 minus negative 1/2 cosine of 2. The 1/2 comes out in front, 1 minus cosine of 2, and there is your exact answer. Okay. Let's go ahead and check that answer to see if it gives us around our estimate of 0.8. 1/2 times 1 minus cosine of 2. Okay, I'm just doing this on my calculator, and we get 0.708. 0.708073. So that is f of 1 exactly. Okay? So that is that question. Now let's return to another question. We can see that as you change x, right, the area is getting bigger and bigger and bigger. We're collecting more and more of that red region. So you can see that the red dot keeps increasing until it reaches a maximum at this value. Okay? What value is that? Where does... Okay, here's a follow-up question. Where does capital F of x have a local maximum? Okay, we can see that there is a local maximum right here, somewhere around 1.5. We can see that from the picture. Okay. Why approximately, if you have a nice graph like that shown on the computer, we have a local maximum at approximately 1.5. How do we know that? How do you find local maximums? You compute the derivative of your function and set it equal to 0 and try to solve for the critical values. What are the critical values? Okay. Well, first you have to find the derivative of the integral from 0 to x of sine of 2t dt. But the answer there, by the second fundamental theorem of calculus, is the sine of 2x. When does the sine of 2x equal 0? Whenever 2x is equal to, remember from the unit circle, that the sine is equal to 0 at 0 and at pi radians. So when 2x is equal to 0, or when, say, 2x is equal to pi, right? And from 2x equal to pi, you figure out that one of your critical values is x is equal to pi over 2. That is one of your critical values. And pi over 2 is approximately 1.5. Okay? So that's what we're seeing here, right at around 1.5, or at pi over 2, your area function, capital F of x, has a local maximum. Okay? So we're going to say more in the next video about how to take derivatives and second derivatives of the area function, right? But I hope this shows you the kinds of questions that can be asked about the area function, okay? And getting used to the meaning of the capital F of x function, the area function, is exactly what we're seeing with this demo, but nothing in this demo we couldn't do by hand, okay? We're just seeing that there is a maximum at around 1.5, and then if you go a little bit more than 5, your area goes negative, so now we have negative signed area, and now we're taking a positive and a negative area, and we're getting a less and less positive number. And if you keep going with this problem, we're getting more and more negative areas, so the total area is decreasing. And then right here, our area function at around pi, at pi exactly, the area function goes to 0 because there is as much area above as there is below. Alright, so the next video will address more of these kinds of questions.